For thousands of years, humans believed that everything in the universe was made of the same basic stuff. The ground beneath our feet, the air we breathe, the stars shining above us at night. It all seemed simple. Matter was matter, light was light, and space, though vast and frightening, felt understandable. But the deeper we looked into the universe, the stranger it became. In the 20th century, scientists built powerful telescopes to study distant galaxies. They expected to see more stars, more glowing gas, more of what they already understood. And they did. But they also discovered something that did not make sense. Galaxies were spinning too fast. According to the laws of physics discovered by Isaac Newton and later expanded by Albert Einstein, objects in space follow predictable rules. If a galaxy spins, the stars near the center should move faster than the stars near the edge. This is how gravity works. In our solar system, Earth orbits the Sun faster than distant planets like Neptune, but when astronomers measured the speed of stars in distant galaxies, they saw something shocking. The outer stars were moving just as fast as the inner ones. They were moving so fast that the galaxies should have flown apart. And yet, they did not. It was as if something invisible was holding them together. One astronomer who studied this mystery closely was Vera Rubin. In the 1970s, she carefully measured how spiral galaxies rotated. Again and again, she found the same result. There had to be far more mass in those galaxies than anyone could see. She proposed that most of the matter in the universe is invisible. It does not glow. It does not reflect light. It does not absorb light. It cannot be seen directly at all. She called it dark matter. Dark matter is not dark like a shadow on the ground. It is dark because it does not interact with light in any normal way, but it does have gravity. And gravity leaves clues. Even if we cannot see something, we can measure how it pulls on other objects. Telescopes like the Hubble Space Telescope have shown that light from distant galaxies bends as it passes through space. This bending, called gravitational lensing, happens because massive objects curve space itself. Einstein predicted this effect long ago, but in many cases, the bending is stronger than it should be. There is not enough visible matter to explain it. Something unseen is adding extra gravity. Over time, the evidence grew stronger. Galaxy clusters were held together by more mass than they contained in stars and gas. Computer simulations showed that without dark matter, galaxies would never have formed the way they did. To date, scientists estimate that everything we can see, stars, planets, gas, dust, and people, makes up only about 5% of the universe. About 27% is dark matter, and nearly 70% is something even stranger, dark energy. In the late 1990s, astronomers studying distant exploding stars discovered that the universe is not just expanding, it is accelerating. Instead of slowing down under gravity, the expansion of space is speeding up. Something is pushing the universe apart. This mysterious force is called dark energy. We do not know what it is. It may be a property of space itself. It may be the new kind of energy field. But whatever it is, it makes up most of the universe. When we look at the night sky, we see glowing stars against blackness. It feels like the light is the main story, but the truth is the opposite. The darkness carries more weight than the light. The universe is structured like a giant web. Galaxies cluster together in long filaments stretching across billions of light years. Between these filaments are vast empty regions called voids. This structure, known as the cosmic web, appears to be shaped by dark matter. Invisible matter forms the framework. Normal matter gathers along it. One powerful piece of evidence came from a system known as the Bullet Cluster. When two galaxy clusters collided, telescopes like the Chandra X-ray Observatory captured glowing gas where normal matter crashed together, but the strongest gravity was found somewhere else. Most of the mass passed straight through the collision without slowing down. That invisible mass lined up with where dark matter should be. Dark matter barely interacts with normal matter. It does not collide easily. It moves through space almost untouched. and yet it shapes galaxies and holds clusters together. Scientists have proposed many ideas about what dark matter might be. It could be made of new particles called WIMP, which interact very weakly with ordinary matter. It could be made of lighter particles called actions. Experiments deep underground are searching for tiny signals of these particles. At places like CERN, scientists smash particles together at high energies, hoping to create or detect something new. So far, dark matter has remained hidden, but it may have shaped the universe from the very beginning. After the Big Bang, tiny clumps of dark matter may have formed first, creating gravitational wells. Normal matter fell into those wells and formed stars and galaxies. In that sense, dark matter may have made our existence possible. Dark energy, meanwhile, may decide our future. If it remains constant, the universe will continue expanding forever. This could lead to a future called heat death. Over trillions of years, stars will burn out. Galaxies will drift apart. Even black holes will slowly evaporate through a process predicted by Stephen Hawking. The universe would become cold, dark, and nearly empty. If dark energy grows stronger, a more dramatic end called the Big Rip could occur. Galaxies would be torn apart. Solar systems would break apart. Eventually, even atoms could be ripped apart as space expands faster and faster. If dark energy weakens, gravity might someday pull everything back together in a big crunch. We do not yet know which path the universe will take. There are even more speculative ideas. Some scientists wonder if dark matter could form dark stars, objects powered not by nuclear fusion but by dark matter interactions. Others consider whether there could be dark galaxies made almost entirely of invisible matter. Some theories imagine a hidden shadow sector of particles and forces. These ideas remain unproven, but they remind us that the universe may be far more layered than we realize. Our galaxy, the Milky Way, is surrounded by a halo of dark matter. Our solar system moves through it. Dark matter particles may be passing through you right now, unnoticed. We are immersed in an invisible ocean, and yet, from this tiny visible fraction of reality, consciousness has emerged. On one small planet, minds have formed that can measure galaxies billions of light years away. We have discovered that we are not at the center of the universe. We have discovered that most of the universe is invisible. We live on a small island of light surrounded by a vast sea of darkness. But we are not blind. We are searching. Every telescope pointed at the sky. Every underground detector waiting in silence. Every equation written on a chalkboard. They are all part of the same effort to understand the unseen. The dark universe is not empty. It is active. It shapes galaxies. It drives cosmic expansion. It may determine the ultimate fate of everything that exists, and we are only beginning to understand it. The unknown is not a small detail in the story of the cosmos. It is the foundation. Space is not silent. For most of human history, we believed it was. When we looked at the night sky, we saw light. We saw stars burning quietly in the darkness. We imagined the universe as a vast, empty vacuum where nothing moved except distant points of fire. But in the 20th century, we discovered something extraordinary. The universe is alive with signals, not sound in the way we hear it on Earth. Sound cannot travel through empty space. There is no air to carry it, but space is filled with electromagnetic waves, radio waves, X-rays, gamma rays, invisible signals constantly traveling across unimaginable distances. Once we learned how to detect them, the silence disappeared. In 1932, an engineer named Karl Jansky was investigating static in radio communications. He built a large rotating antenna and noticed something strange. There was a steady hiss of radio noise that came from the sky. At first, he thought it might be interference from storms, but the signal repeated every 23 hours and 56 minutes, the exact time it takes for the stars to return to the same position overhead. The signal was coming from the center of our galaxy, the Milky Way. Humanity had just discovered radio astronomy. Suddenly, the universe was no longer dark and quiet. It was broadcasting. As radio telescopes grew larger and more sensitive, they began detecting strange objects called pulsars. In 1967, a graduate student named Jocelyn Bell Burnell noticed an unusual repeating signal in her data. It was a series of radio pulses arriving with perfect regularity, one pulse every 1.3 seconds. The signal was so precise that, for a brief moment, scientists considered a shocking possibility. Could it be artificial? Could it be a signal from an intelligent civilization? The team jokingly labeled it LGM-1, short for Little Green Men, but further study revealed a natural explanation. The signal came from a rapidly spinning neutron star, the collapsed core of a massive star that had exploded. As it rotated, beams of radiation swept across space like a lighthouse. Each time the beam crossed Earth, we detected a pulse. The mystery was solved, but it planted an idea. If nature could produce signals that looked artificial at first glance, what else might be hiding in the noise? For decades, scientists have scanned the skies for unusual radio signals. Organizations like the SETI Institute have dedicated themselves to searching for patterns that cannot be explained by known astrophysical sources. The idea is simple. If an advanced civilization exists somewhere in the galaxy, it might use radio waves to communicate. Radio waves travel far. They can pass through dust and gas. They are relatively easy to generate. All we have to do is listen. And sometimes we hear things we cannot easily explain. In 1977, a radio telescope at Ohio State University detected a powerful, narrowband radio signal that lasted for 72 seconds. It was strong. It matched what scientists expected from an artificial transmission. When astronomer Jerry R. Ayman reviewed the data printout, he circled the signal and wrote one word beside it. Wow. It became known as the WOW signal. The signal has never been detected again. Despite decades of searching, no clear explanation has been confirmed. Some scientists suggest it may have been a natural event, perhaps a passing comet or a rare astrophysical burst. Others believe it remains unexplained. It is a reminder that the universe still surprises us. In recent years, a new mystery has emerged, one that is even stranger. They are called fast radio bursts. Fast radio bursts, or FRB, are extremely powerful pulses of radio energy that last only milliseconds. In that tiny fraction of a second, they can release as much energy as the sun emits in days or even weeks. The first FRB was discovered in 2007 by astronomer Duncan Lorimer and his student. At first, many scientists thought it might be an error in the data. The burst was so bright and so brief that it seemed almost impossible, but more were found. Some FRBs appear only once and never repeat. Others repeat in strange patterns. One repeating source was traced to a small galaxy billions of light-years away. Another was linked to our magnetar, a highly magnetic neutron star within our own galaxy. Magnetars are among the most extreme objects in the universe. They are the collapsed cores of massive stars packed into a sphere only about 20 kilometers wide. Their magnetic fields are trillions of times stronger than Earth's. When their magnetic fields shift or crack, they can release bursts of energy powerful enough to be detected across galaxies. In 2020, a magnetar in the Milky Way produced a burst that matched the energy pattern of some FRBs. This was strong evidence that at least some fast radio bursts come from magnetars, but not all of them fit neatly into that explanation. Some FRBs repeat in complex cycles. Others originate in environments that seem unusual. The diversity of their behavior suggests that there may be more than one cause. For a brief time, speculation exploded across the internet. Could FRBs be artificial? Could they be signals from advanced civilizations? Most scientists remain cautious. Natural explanations are still far more likely, But the fact remains, we are detecting powerful, distant signals that were completely unknown just a few decades ago. The universe is not just glowing, it is flashing, and we are only beginning to understand the language. Beyond radio waves, space is filled with other invisible messengers. Gamma-ray bursts are among the most energetic events ever observed. They appear suddenly, shine intensely, and fade within seconds. These bursts are believed to be caused by massive stars collapsing into black holes or by neutron stars colliding for a few seconds. A gamma-ray burst can outshine entire galaxies. If one occurred too close to Earth, it could damage our atmosphere. It could threaten life itself. Fortunately, most of them occur billions of light years away. Still, their existence reminds us that the cosmos is not calm. It is violent. It is unpredictable, and sometimes it sends signals that travel across space for millions or billions of years before reaching us. When we detect these signals, we are looking into the past. A radio pulse that arrives today may have begun its journey before humans existed. A gamma-ray burst detected tonight may have started before Earth formed. Every signal is a time capsule, and somewhere within the endless stream of cosmic noise, there may be patterns we have not yet recognized. Our instruments are improving. New radio arrays span deserts and valleys. Space telescopes scan high-energy radiation from orbit. Artificial intelligence now helps search through enormous amounts of data, looking for signals that humans might miss. We are listening more carefully than ever before, and the universe keeps whispering. Some signals we understand, some we partially understand, some remain mysteries. The void is not empty. It is speaking. The question is whether we can learn to understand what it is saying. In October of 2017, astronomers working with a telescope in Hawaii noticed something unusual moving across the sky. At first, it looked like a faint point of light, drifting slowly against the background stars. But as they tracked it more carefully, they realized this object was not orbiting the sun like a normal asteroid or comet. It was moving too fast, and its path was strange. The object was eventually named Aumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and that name turned out to be fitting. Aumuamua was not from our solar system. It had entered from interstellar space. For the first time in human history, we had detected an object passing through our solar system that originated around another star. That alone would have been historic. But Aumuamua quickly became one of the most mysterious objects ever observed. First, its shape appeared unusual. Based on how its brightness changed as it rotated, astronomers concluded that it was extremely elongated, possibly shaped like a cigar or even a pancake. It was unlike typical asteroids we have studied. Second, it behaved strangely. As Aumuamua moved away from the sun, it slightly accelerated. Normally, comets accelerate when sunlight heats their icy surfaces, causing gas to escape and push them like a rocket. But telescopes did not detect the usual signs of a comet. No visible tail, no obvious gas cloud. It was accelerating, but without clear evidence of outgassing. This raised serious questions. Most scientists proposed natural explanations. Perhaps Aumuamua was made of unusual materials. Maybe it was coated in a thin layer of hydrogen ice that evaporated invisibly. Maybe it was a fragment of a larger object torn apart in another star system. But one scientist suggested a more dramatic possibility. Avi Loeb, a Harvard astronomer, proposed that Aumuamua could be artificial, perhaps a piece of alien technology, maybe even a kind of light sail propelled by radiation pressure from stars. His suggestion sparked intense debate. Most astronomers remain skeptical of the artificial explanation. Natural causes are still considered far more likely, but the idea captured public imagination for a simple reason. Aumuamua did not fit comfortably into known categories. It reminded us that we are not alone in space, not in the sense of aliens, but in the sense that objects from other star systems move through our neighborhood, and sometimes they do not behave exactly as expected. In 2019, another interstellar object was detected, 2I/Borisov. Unlike Oumuamua, this one behaved clearly like a comet, with visible gas and dust streaming behind it. It reassured scientists that interstellar visitors may be common and usually natural, but the mystery of Oumuamua remains only partially resolved. It was a messenger from another system, and it did not stay long enough for us to fully understand it. The discovery of interstellar objects changes how we see the solar system. For centuries, we thought of it as isolated planets orbiting our sun in a closed system. Now we know that material from other stars passes through from time to time. Our solar system is not a sealed bubble. It is part of a larger cosmic environment. And this raises an intriguing possibility. If rocks can travel between stars, could something else? Could life travel that way? Could microscopic organisms survive inside protected rocks, drifting through space for millions of years before landing on a planet? This idea is called panspermia. While there is no proof that it has happened, it remains scientifically possible. The boundaries between star systems may be more porous than we once thought. Meanwhile, the search for artificial signals continues. The SETI Institute and other research groups scan the sky for technosignatures, signs of advanced technology beyond Earth. These could include narrow radio signals, unusual laser pulses, or even large-scale structures built around stars. One famous concept is the Dyson sphere, proposed by physicist Freeman Dyson. He suggested that an advanced civilization might build a massive structure around its star to capture energy. Such a structure could change the star's light in detectable ways. Astronomers have searched for unusual stars that dim in strange patterns. One such object, known as Tabby's star, briefly caused excitement when it showed irregular dips in brightness. Some wondered if it could be evidence of a megastructure, but further studies suggested that dust was the more likely explanation. Again and again, nature offers strange signals. Again and again, natural explanations eventually emerge. But the process matters. Each mystery forces us to test our understanding. Each unexplained signal pushes us to build better instruments, ask better questions, and examine assumptions. Even when the answer turns out to be ordinary physics, the path to that answer expands our knowledge. And yet, the possibility remains. The universe is enormous. The Milky Way alone contains hundreds of billions of stars. Beyond it lie billions of other galaxies. Statistically, it seems unlikely that Earth is the only planet where life has emerged, but distance is a powerful barrier. Signals weaken over light years. Civilizations may rise and fall in cosmic moments. The window during which two intelligent species overlap and communicate may be small, so we listen, not because we expect certainty, but because silence would be worse. Fast radio bursts continue to challenge us. Some repeat with patterns that are not fully understood. Some originate in dense, extreme environments. Others appear to come from quieter regions of space. Each burst lasts only milliseconds, yet within that brief flash lies information about magnetic fields, plasma, and intergalactic space. As the radio waves travel billions of light years, they pass through clouds of charged particles. This slightly delays different frequencies, allowing scientists to measure how much material lies between galaxies. In this way, even mysterious signals become tools. They help map the invisible matter between galaxies. They help reveal the structure of the universe. Signals from the void are not just puzzles, they are probes, and sometimes they remind us how young our understanding truly is. Just a century ago, we did not know that galaxies beyond our own even existed. Astronomer Edwin Hubble showed that faint spiral shapes in the sky were entire galaxies far beyond the Milky Way. That discovery expanded the known universe overnight. Today, we are in a similar phase. We are detecting phenomena, FRB, interstellar visitors, unusual stellar dimming that we did not know existed a few decades ago. Some will turn out to be natural, some may reveal entirely new physics, and somewhere within the endless static of space, there may still be the signal we have not yet recognized. The universe is not quiet. It crackles, it flashes, it hums with energy, and in that vast symphony of radiation and motion, we are learning to listen. For most of human history, we understood the universe through sight. We looked up and saw stars. We built telescopes and saw more stars. Even when we began detecting radio waves and X-rays, we were still observing forms of light. Different wavelengths, invisible to our eyes, but still light. Then, in 2015, humanity heard something new, not with ears, but with instruments sensitive enough to detect the movement of space itself. At an observatory called LIGO, scientists confirmed the first detection of gravitational waves. These waves were not made of light. They were ripples in space-time, tiny distortions caused by massive objects accelerating through the universe. The signal came from two black holes colliding more than 1 billion light-years away. For a fraction of a second, those black holes spiraled around each other at incredible speed. When they merged, they released energy not just as radiation, but as vibrations in the fabric of reality itself. By the time the ripples reached Earth, they were unbelievably small. They stretched and squeezed space by less than the width of a proton, and yet our instruments were precise enough to measure them. For the first time, we were not just seeing the universe, we were feeling it. This marked the beginning of gravitational wave astronomy. Black holes, once considered completely silent, were suddenly speaking. Black holes are among the most mysterious objects in existence. Formed when massive stars collapse under their own gravity, they contain so much mass in such a small space that not even light can escape. The boundary around them is called the event horizon, the point of no return. At the center of nearly every large galaxy lies a supermassive black hole. At the center of our own Milky Way is one called Sagittarius A*. For decades, black holes were theoretical objects predicted by Einstein's equations. Then evidence began to pile up. Stars near the center of the Milky Way were orbiting something invisible and incredibly massive. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow in a distant galaxy. In 2022, it released an image of Sagittarius A* itself. Black holes were no longer just mathematical predictions. They were real, and they were loud. When two black holes merge, they release gravitational waves that travel outward in all directions. These waves carry information about the mass and spin of the objects that created them. By studying these signals, scientists can measure black holes that would otherwise be invisible. Gravitational waves opened a new sense for humanity. For centuries, we relied on vision. Now we had something like touch, a way to detect cosmic vibrations, and this new sense may reveal mysteries we have not yet imagined. Some gravitational wave signals are simple and clear, the clean chirp of two black holes merging. But as detectors become more sensitive, we may begin hearing more complex patterns. Collisions between neutron stars, black holes swallowing smaller objects, perhaps even signals from the early universe itself. There is a theory that moments after the Big Bang, the universe may have produced gravitational waves. If we detect them, they could provide clues about how everything began. Signals are not limited to radio waves or gravitational ripples. High-energy particles constantly bombard Earth from space. These particles, called cosmic rays, travel at nearly the speed of light. Some originate from supernova explosions. Others may come from active galactic nuclei, regions around supermassive black holes that blast jets of radiation across space. In 2017, a powerful neutrino, a nearly massless particle, was detected by an observatory in Antarctica called Ice Cube Neutrino Observatory. Scientists traced it back to a distant galaxy with a supermassive black hole actively consuming matter. Neutrinos are extremely difficult to detect. They pass through planets, stars, and entire galaxies almost without interacting. Trillions pass through your body every second. Yet when one is detected, it is a messenger from deep space. We are no longer limited to light. We are listening through gravity. We are detecting through neutrinos. We are mapping through radio bursts. The universe communicates in many ways, and sometimes the signals do not fit neatly into our expectations. Certain fast radio bursts repeat in cycles. One source appears to turn on and off in a predictable rhythm. Another shows bursts clustered in patterns that scientists are still trying to decode. The repetition is not regular like a pulsar, but not completely random either. It is somewhere in between. When faced with patterns, the human brain searches for meaning. We evolved to recognize shapes and rhythms. Sometimes this leads to breakthroughs. Sometimes it leads to false conclusions. The challenge in astrophysics is to remain patient, to gather more data, to test every natural explanation before considering extraordinary ones. But even natural explanations can be extraordinary. A magnet releasing bursts of energy across billions of light years is not ordinary in any everyday sense. A black hole merger bending space-time is not simple. An interstellar object drifting between stars is not common in human experience. The universe is more dramatic than fiction, and yet it operates according to physical laws. There is another mystery tied to signals, the limits of communication itself. Even if an advanced civilization exists somewhere in our galaxy, distance is a major obstacle. The Milky Way is about 100,000 light-years across. A signal sent from one side would take 100,000 years to reach the other. A conversation would span ages. Civilizations may not last that long. Technologies may change. Signals may fade. We might be listening at the wrong time, or on the wrong frequency. Or perhaps the universe is simply quiet in terms of intelligent broadcasts. The silence itself is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is common, why have we not detected it?" There are many possible answers. Intelligent life may be rare. Civilizations may destroy themselves. They may choose not to broadcast. They may use communication methods we have not yet discovered, or they may be too far away. For now, the signals we detect, FRB, gravitational waves, neutrinos, gamma-ray bursts, all appear to have natural explanations. But each discovery expands the boundary of the unknown. Each time we build a more sensitive instrument, the universe reveals something new. A century ago, radio astronomy did not exist. 50 years ago, we did not know about fast radio bursts. 10 years ago, we had never directly detected gravitational waves. What will we discover next? Somewhere in the static of the cosmos, there are signals still waiting to be recognized, patterns buried in noise, events too faint for current detectors, ripples too subtle for today's instruments. The void is not empty, it is active. It flashes with radio bursts, it trembles with gravitational waves, it rains particles from distant galaxies, and we are learning, slowly, to interpret its language. The question is not whether the universe is speaking, it is whether we are ready to understand. The universe has a long memory. Every signal that reaches us has traveled for millions, sometimes billions of years. A single burst of energy, a flash of light, a ripple in space-time, all of it is history arriving late. When we detect a fast radio burst, we are listening to a voice that left its source long before humans existed. When a gravitational wave hits Earth, we feel an event that happened before life even appeared on Earth. Time and distance in space are enormous barriers. That is why searching for intelligent signals is so difficult. Even if civilizations broadcast messages, the vastness of the galaxy means most signals will never reach us. And if they do, they may arrive long after their creators are gone. A civilization might rise and fall within a few thousand years, a cosmic blink, leaving behind a faint whisper we may detect only by chance. This long delay forces us to think differently about communication. It is not like talking across a room. It is more like listening for echoes from the dawn of time, and those echoes are often hidden in noise. Scientists call this the search for technosignatures. These are signs of technology beyond Earth. Unlike natural phenomena, technosignatures might indicate intelligence, radio beams, laser flashes, or patterns in light that cannot be explained by physics alone. Searching for them requires patience, creativity, and caution. Many signals that initially seem unusual eventually turn out to be natural, but some remain unexplained, and they push our understanding forward. One of the most intriguing examples is the object known as Oumuamua. Continue. Black holes are often thought of as cosmic vacuums, swallowing everything around them, leaving nothing behind. But in reality, they can also be loud. When matter falls into a black hole, it does not disappear silently. It accelerates, heats up, and releases enormous energy. Some of this energy escapes as jets of particles moving close to the speed of light. These jets shine across the universe in X-rays, gamma rays, and sometimes radio waves. Even though the black hole itself is invisible, these signals act like a beacon, telling us where it lies and what it is doing. Supermassive black holes, which sit at the center of galaxies, are especially dramatic. Some of them actively consume gas and dust, forming what are called active galactic nuclei. Their jets can extend for millions of light years, impacting the formation of stars and the evolution of galaxies. By studying the signals emitted from these jets, astronomers can map the dynamics of galaxies, measure magnetic fields, and even probe the behavior of space-time near the event horizon. And then there are the mysterious patterns of certain fast radio bursts. Some repeat on schedules that are strange and irregular. Others appear to cluster in ways that defy simple explanation. Scientists have proposed explanations ranging from magnets interacting with surrounding plasma to colliding neutron stars. But there is no single answer yet. Each repeating FRB seems to have its own personality, as if the universe is sending messages with its own unique code. Gamma ray bursts add another layer of mystery. They are among the most energetic events ever detected. A single burst can release as much energy in a few seconds as the sun produces in its entire lifetime. Most originate from collapsing massive stars or merging neutron stars, but some are still unexplained. These bursts can serve as probes of the early universe, revealing the presence of matter and magnetic fields billions of years ago. Neutrinos, the ghostly particles that pass through planets and stars without interacting, are yet another messenger. When detected, they provide information about the most extreme processes in the universe, exploding stars, colliding black holes, or perhaps sources we have yet to imagine. The Ice Cube Neutrino Observatory in Antarctica has already traced neutrinos to distant galaxies, opening a new window on the cosmos. All of these signals, FRB, gamma rays, neutrinos, gravitational waves, are pieces of a puzzle. Individually, they tell us a fragment of the story. Together, they begin to reveal a picture of a universe that is dynamic, violent, and interconnected in ways we are only beginning to understand. Yet, the universe also teaches humility. Signals arrive faintly, often delayed by millions or billions of years. Some fade before we can study them. Others are hidden in noise, indistinguishable from the background hum of the cosmos. Some may be entirely beyond our ability to detect. This is the nature of exploration. The unknown is vast, and our tools are limited. But every new discovery, whether a repeating FRB, an interstellar visitor like Oumuamua, or a gravitational wave from a distant black hole merger, expands the horizon of human understanding. Listening to the universe is not just about collecting data. It is about learning patience, curiosity, and wonder. Each signal is an invitation to ask new questions, to refine theories, and to imagine possibilities beyond current knowledge. The void is not empty. It is alive with motion, energy, and information. It sends pulses, flashes, and ripples across unimaginable distances. And within those signals, we catch glimpses of the extraordinary, the extreme physics of neutron stars, the birth and death of stars, the invisible scaffolding of dark matter, and perhaps even signs of intelligence we have yet to recognize. The cosmos speaks in a language we are only beginning to learn. Sometimes it is subtle, sometimes it is dramatic, but it is always there, waiting for us to listen. Segment 2 ends here, leaving us with more mysteries than answers, but also with a profound sense of wonder. We have explored the universe as it speaks through signals, from the faint radio hisses first detected by Carl Jansky to the gravitational waves that ripple space-time itself. Each discovery has expanded our understanding and reminded us that the unknown is the true canvas of the cosmos. The universe is vast, far beyond anything we can truly imagine. When we look up at the night sky, we see only a tiny fraction of what exists. Stars that shine, planets that orbit, and galaxies that glow are the visible tip of a cosmic iceberg. Beneath that faint light lies a dark, mysterious, and largely invisible world, a world that shapes everything we see, yet remains almost entirely unknown. Black holes are among the most enigmatic of these shadows. They are regions where gravity is so strong that nothing, not even light, can escape. Formed from the collapse of massive stars, black holes come in various sizes, from a few times the mass of our sun to billions of times heavier. Their presence is betrayed only by their effects on nearby matter. Gas, dust, and even stars spiral toward them in what is called an accretion disk. As material falls inward, friction and gravitational forces heat it to millions of degrees, emitting X-rays and gamma rays detectable from Earth. But black holes are not only destructive, they are also messengers. When two black holes collide, they create gravitational waves, ripples in space-time that travel across the universe. These waves carry information about the masses, spins, and orbits of the merging black holes. By detecting and analyzing them, scientists can reconstruct cosmic events that happened billions of years ago, long before Earth existed. Supermassive black holes, which sit at the centers of galaxies, are even stranger. Our own Milky Way is home to Sagittarius Asterisk, a black hole about 4 million times the mass of the Sun. Though invisible directly, its gravity governs the orbits of nearby stars. Observations of these stars allowed astronomers to confirm its mass and infer its presence decades before we could even imagine photographing a black hole. Black holes warp space and time around them. This warping creates extreme environments where the laws of physics approach their limits. Close to a black hole, time slows relative to distant observers, light is bent, and matter can be stretched and compressed in ways that seem almost unimaginable. It is a natural laboratory for testing Einstein's theory of general relativity under the most extreme conditions. Beyond black holes, the universe is full of wandering objects that defy easy categorization. Rogue planets drift through space without a parent star. Comets and asteroids occasionally enter our solar system from interstellar space, like Oumuamua in 2017. Each of these travelers carries clues about other star systems, planetary formation, and perhaps even the possibility of life beyond Earth. The edges of our observable universe also hold profound mysteries. Light from the most distant galaxies takes billions of years to reach us. Observing them is like looking back in time, seeing galaxies as they existed shortly after the Big Bang. But beyond the observable universe, space may extend infinitely, possibly containing regions with physics, matter, or life entirely different from what we know. Dark matter and dark energy dominate this hidden realm. Dark matter provides the gravitational scaffolding that holds galaxies and clusters together. Dark energy drives the accelerating expansion of the universe, pushing galaxies farther apart over time. Together, they make up over 95% of the cosmos, yet their true nature remains unknown. Quantum mysteries also creep into the cosmic shadows. Even empty space is not empty. Quantum fluctuations create temporary particles that pop in and out of existence. These fluctuations may have influenced the early universe, seeding the structure of galaxies and clusters we see today. At the smallest scales, space and time themselves may be discrete rather than continuous, a property we have yet to fully understand. Some scientists speculate that black holes might even be connected to other regions of space through phenomena called wormholes, hypothetical shortcuts through space-time. While purely theoretical at this point, wormholes tantalize us with the possibility of travel or communication across vast cosmic distances, or even between parallel universes. The universe communicates with us in countless ways: light, gravity, neutrinos, cosmic rays, and mysterious bursts like FRBs are all part of a complex cosmic conversation. Some signals tell us about violent events, stars dying, black holes merging, galaxies colliding. Others may be subtle, carrying information about the unseen structures of space, like dark matter halos or magnetic fields threading intergalactic space. Our challenge is to listen and interpret. Each signal we detect expands our understanding and often raises new questions. Some may be caused by phenomena we already know, but many may point to physics beyond our current theories. Every anomaly is an invitation to explore, to think differently, and to recognize that our knowledge is limited but growing. And as we peer into these cosmic shadows, we begin to understand something profound. The universe is far stranger and more complex than we ever imagined. For every answer we uncover, dozens more mysteries emerge. The cosmos is a puzzle with pieces scattered across space and time, waiting for human curiosity, ingenuity, and persistence to assemble. Neutron stars are among the most extreme objects in the universe, formed when massive stars collapse after supernova explosions. They pack more mass than our sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. Their gravity is intense, their density unimaginable, and their magnetic fields trillions of times stronger than the sun's. Some neutron stars spin hundreds of times per second, emitting beams of radiation from their magnetic poles. If these beams sweep past Earth, we detect them as pulsars, incredibly precise cosmic clocks. Pulsars are so consistent that scientists use them to test theories of gravity, map interstellar space, and even plan navigation for future spacecraft in deep space. Other neutron stars, called magnetars, take the extremes even further. Their magnetic fields can twist and snap the atoms themselves. When a magnetar's field fractures, it releases bursts of energy visible across galaxies. Some fast radio bursts are now thought to originate from magnetars, linking these mysterious flashes to one of the universe's most exotic objects. Cosmic voids, the enormous empty regions between galaxies, also hold secrets. These voids are vast expanses with very few stars or galaxies, stretching millions of light years across. While they appear empty, they influence the movement of galaxies around them. They are laboratories for studying dark energy, the mysterious force driving the universe's accelerating expansion. Observing voids helps scientists understand how matter and energy are distributed on the largest scales and may eventually provide clues about the ultimate fate of the cosmos. At the largest scales, the universe forms a web-like structure. Galaxies are not randomly scattered, they cluster along filaments of dark matter with immense voids between them. This cosmic web reveals the fingerprints of the Big Bang and the behavior of matter over billions of years. By mapping it, we can learn about the universe's expansion, the influence of dark energy, and how structures evolve over time. Time itself becomes a curious player in the cosmic stage. Near massive objects like black holes, time slows relative to distant observers, a phenomenon called time dilation. In neutron stars and black holes, these effects are extreme. A few hours near a black hole could correspond to years elsewhere. This reminds us that our everyday experience of time is not universal. It is shaped by gravity and motion. Entropy, the measure of disorder in a system, also governs cosmic evolution. Stars burn fuel and die. Galaxies collide. Black holes grow, and matter disperses. Over billions of years, the universe becomes more entropic. Eventually, if current theories hold, stars will burn out, galaxies will drift apart, and the cosmos may approach a cold, dark, diffuse state known as the heat death. Yet even as the universe trends toward disorder, it continues to produce remarkable phenomena: collapsing stars, colliding neutron stars, interstellar wanderers, and bursts of energy across space. The cosmos is a balance of chaos and structure, randomness and pattern, destruction and creation. The interplay of dark matter, dark energy, and ordinary matter remains one of the greatest mysteries. Dark matter provides the gravitational scaffolding that holds galaxies together, yet we cannot see it directly. Dark energy drives cosmic acceleration, yet we do not know its origin. Ordinary matter, the stars, planets, and galaxies we observe, makes up only a small fraction of the total. The invisible majority governs the behavior of the universe in ways we are only beginning to understand.